Okay, so what we're going to be looking at here in this particular section, we're going to be looking at a new idea that we haven't really discussed before. This is going to be your first calculus idea, and this is the basis for a lot of the things that we talk about in the rest of this class. So although this might not seem like it's something that's incredibly difficult, it is difficult enough that we need to look at it. What you're going to do is actually not that hard. Rather than me just droning on about it, let's just take a look at what's going on, okay? So the first thing that I kind of want to look at is if we had this function f of x equals x squared plus 4. If I were to take and evaluate each of these functions, what I would find is if I take 2 and I plug it in, 2 squared is 4 plus 4 is 8. Now if I were to take 2.1 and plug that in, and then plug in 2.01 and 2.001 or 2.0000001, or in the other direction, what we would find is as these x values get closer and closer to 8 with our calculator, so I just take these and plug them in. So if I had like 2.01 squared plus 4, what we would get is not actually 8. I believe what we get here is 8.0104, I believe is what we get if we were to do that. And I could be wrong about that as far as what number you get. But the closer, the idea that I'm trying to show you here is the closer our x values get to 2, when we're trying to evaluate our function, that means our function value should be getting closer and closer to 8. And I know that sounds like just not a dumb idea necessarily, but it's an idea that you're like, well, no, duh. If I'm looking at a graph, like this graph, like here's a picture of this graph. As I look at this graph, I can see right here, this is where x equals 2. So if I try and evaluate this function, when I plug in 2, I get 8. And we talked about that before, and that's why it appears on the graph. But as my x values get closer and closer and closer to 2 from either direction, either slightly bigger than 2 or slightly smaller than 2, then the closer I get to x equals 2, the closer my function values get to x equals 8. And if I were to plug in a number, and you could try this on your calculator, if you were to take like 1.9999999 and just push a whole bunch of 9s in there, like 20 9s, and put that in and try and evaluate this function, what your calculator would spit out it would spit out 8, even though that's not technically the answer. Your calculator's just like, you know what? The answer here is so close to 8 that we can basically say that it is 8 for all intents and purposes. Now, I know a lot of people are like, that seems really stupid, because if I want to know what y value I'm going to get when I get really close to an x value, and I'm talking really close here. We're not talking like 2.01. We're talking like 2.0000001. It's so close to 2 that what we basically say is, you know what? Whatever number I get when I plug in 2, I'm getting super close to that value, so I'm just going to say that that's what it is. Now, what we've done here, and it doesn't seem like we've done anything other than kind of go in a circular motion, but what we've done here is we have done what is known as evaluating a limit. Finding a number that is finding a y value that is really close to another one by evaluating using an x value that is really close to the one that we are interested in. This idea seems really stupid. You're like, why would I even care about that? Especially when you see how to do these problems in just a second. You're going to be like, that's really dumb. But this really is the basis for all of calculus. It's the underlying idea. Limits are involved in everything in calculus, even though we won't use them extensively in this course, and you'll see why as we get further into it. Limits are very important. Okay? So the first thing that we need to talk about is we need to talk about how a limit is written. You will see almost every limit problem written like this, where you will see the letters LIM, and then you will see below it x with an arrow pointing to some number. So this is just any number. I'm just going to put some number right there. And then we are going to see some function. And we'll just call that function f of x in this case. The way that we say this is, first of all, anytime you see LIM, we say that we are going to evaluate the limit. So when you see that, the first thing you say is we are going to evaluate the limit. The next part, where we have x with an arrow pointing to a, the way that we say that is we say x approaches a. What that means is, just like we talked about before, if we are interested in the y values really close to a specific function value, we need to know what x value it is that we are getting really close to. And in this case, that would be the number. So the way that we say this thus far is the limit as x approaches a. And then lastly, we're always going to have some sort of function on the very end. of the limit. And so how we say this in general is the limit as x approaches a of f of x, whatever that function is. So here's a couple of examples, okay? The way that we would say this first problem is we would say this is the limit as x approaches 1 of x squared plus 2x plus 1. Now what this is asking us is, what is the y value we are getting really close to when x gets really close to 1 on this function? Well, what we want to know is, in reality, is all we really have to do is I want to know what I'm getting close to, so I'm just going to take 1 and I'm going to plug that in. So I'm going to plug 1 in there. 1 plus 2 plus 1 is 4. What this is saying is, as x gets really close to 1 on this particular function, then y gets really close to 4. And that's your answer. You don't have to do anything special with it. You just say, you know what, I'm getting really close to 4. And that is always the first step when we evaluate a limit. Like when I have x approaches 4 here, I would just say, plug that limit in, the number in for x. So I get 4 squared, which is 16, minus 15, which is 1. 16 minus 15 is 1. That is my limit here. Okay, that is the y value I'm getting really close to as x approaches 4. The next one is, it's the limit as x approaches 7. Again, hopefully you've got this down by now. You just take that x value, you plug it in, and in this case, 42 minus 35 is 7, so that would be that particular limit. That's the y value we're getting really close to. So you're probably thinking, okay, this is just stupid. Like, this is exactly the same as evaluating a limit, like doing f of 1. So the next question we have to ask ourselves is, does a limit always equal the function value? And rather than having a long conversation about that, here's kind of how you have to think about it. Let's say I had a function and it had a hole in the graph somewhere along the line. Now, a hole in the graph just means at one particular x value, I'm just going to make this up, let's say that's x equals 3. So in this particular example, the function value does not exist because there's a hole in the graph right there. So f of 3 does not exist here. However, if I were to look at the limit as x approaches 3 of f of x in this case, then I would say, okay, you know what? Let's say that hole is at the point 3, 2. I could say that as I get really, really close to 3, like if I look at x equals 2.99999 or x equals 3.00001, that those y values, if I was to evaluate the function there, are getting really, really, really close to x, or to y equals 2. So even though the function value there is no function value for f of 3, the limit as x approaches 3 does equal 2. So all of a sudden, this idea of a limit takes on a slightly new meaning, because now we're saying, okay, what is the y value when we get really close to a particular x value, which is a new idea. Before we just said the function doesn't exist at that point. Now we say that the limit does exist. So you might be saying, okay, well, where is that going to help me? Well, when I look at a function like this, f of x equals x squared minus 4 over x minus 2, if I were to graph this, this is what my calculator would spit out. It would just spit out a straight line, okay? But as you recall from last year, if this factors down, the top factors down, and there is a factor on the top that matches a factor on the bottom, like in this case x minus 2, then we can say that at x equals 2, there is a hole in the graph. But if you use your calculator or Desmos or something else to graph something on a calculator, you'll find out really quickly that that holes do not show up. They don't show up when you graph them. So the graph looks like it still exists there, but at x equals 2, there is nothing, there is a hole in the graph, so the function does not exist. And I'm sure that's exactly how you feel, okay? So we can see and we know by looking at the graph that our limit is going to equal 4. We just talked about that. You look at this graph, it looks like the y value is 4, even though there's a hole in the graph as I approach 2. So what we do when we have a limit problem is just the same thing we did on those other ones, even though we know there's going to be a hole in the graph. I take 2, I plug it in. And when I do that, I get 0 divided by 0. Now, 0 divided by 0, normally you'd be like, oh, you can't divide by 0. And that is always true. However, when we are looking at a limit, we're not actually plugging in 2. We're actually plugging in a number that is really, 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 really close to 2. And when I do that, 2 this number that's really close to 2 minus 2 doesn't actually give us 0. So it's entirely possible that the limit still exists, we just don't know what it is based on what we have so far. When we get this, what happens is we get what is known as the indeterminate form. The indeterminate form is anytime I get 0 over 0, that means the limit might still exist, I just don't know what it is and I have to go about finding it a different way. Okay, and that's what this is saying right here. The indeterminate form, it just means, okay, we do not know exactly what that limit is just yet. Okay, but we can find it. And the way that we find it, or at least the way we find it right now, and we'll learn a different way later in the class, is we say, you know what? That graph that I looked at before looks exactly like a line. Okay, it looks just like a line. And the reason why it looks like a line is if I factor this down and cancel out the like terms from the top and the bottom, I am left with x plus 2, which is exactly what this graph looks like, except it doesn't have a hole in it. So the idea is we are going to evaluate this limit of a function that looks identical to our original one, other than there is not a hole in this particular graph of x plus 2. So I can evaluate it the old-fashioned way by just plugging in 2. 2 plus 2 is equal to 4. And that means that once and I guess what I'm trying to say here is, what we do, if we have the indeterminate form, is we factor whatever we can and see if something cancels from the top and the bottom. If it does, then we take our new function after everything is canceled and try and evaluate our limit again. Once we do that, then, and usually it works, the part that's causing us the 0 over 0 is going to go away, and we're left with a way that we can actually find out what that limit is without resorting to looking at the graph, because you can't always look at the graph. Sometimes you don't have a calculator. So that's what we do with the indeterminate form. So here's another one. If I take 5 and I plug this in, I get 5 squared minus 25 over 5 minus 5. That's 25 minus 25 over 5 minus 5, which is 0 over 0. Because this is a limit, the number that we're plugging in is not actually 5, but a number that's really close to 5, so we have the indeterminate form. And we remember that this factors down to x minus 5 times x plus 5. And I can see the x minus 5's cancel, so I am left with the limit as x approaches 5 of x plus 5, which is 10. That's how we deal with the indeterminate form. And there are actually more versions of the indeterminate form that we will revisit as we get further into this class. Now, there are certain times where we still cannot evaluate a limit. One of those is if you take a square root of a negative number. If you evaluate a limit and you get the square root of a negative number, it still doesn't exist. We still cannot do that. You also cannot take the logarithm of a non-positive number. You'll notice this sounds familiar because this is the exact same thing we had when we were talking about domain. The third thing you cannot do is you cannot divide just by 0. I know the indeterminate form had 0 divided by 0, but if you get like 4 divided by 0 or 7 divided by 0, then you cannot evaluate that limit. And if any of those happen, and this is a video for Mean Girls, and you can go watch it sometime if you want, but basically what we say is that the limit does not exist. So if I have a problem like this, where I try and evaluate this, I get 1 over 3 squared minus 9, which is 1 over 9 minus 9, which is 1 over 0. Notice that is not the indeterminate form. It's not 0 over 0. So we say that does not exist. That limit simply does not exist because we are not getting close to a specific y value in this instance. If I get this one, I try and evaluate by plugging in the limit. I get the square root of negative 2. Cannot take the square root of a negative number, so we say does not exist. Anytime we get functions where we're still violating those same rules we talked about before, we just say, oh, that limit, we can't do that limit, and we say the limit does not exist. So if you want a summary of what we do in order to evaluate a limit, here are your 3 steps. The first thing you do is always plug that x value in to evaluate the limit, because you have to know whether or not you have the indeterminate form. If you get a number answer, congratulations, you have your limit. If you get 0 over 0, then you have the indeterminate form, and you need to move on and do one more step to try and evaluate the limit. What you do once you have the indeterminate form is you factor both the top and the bottom of the function, and once you do that, you see if anything cancels out. You cancel those things out, then you try and evaluate the limit again by plugging in that exact same number, and if you get a number answer out, then congratulations, you have evaluated the limit correctly. Now, we're definitely going to talk more about limits in this class and how they are so important to us, but this is an introduction to what a limit is. If you have any questions, please come on in and ask me, and I'm more than willing to help you with anything that you need.